I'm going to present HashTag. In HashTag, we try to combine memory tagging and DRAM integrity protection. Now, just yesterday, there was a track about memory, and there were some talks that used memory tagging. So this is great, because this kind of justifies what we are doing here. Memory tagging is a really cool feature. It's hardware-enforced security, and we can mitigate a lot of memory safety issues by using memory tagging. However, we have this problem that it induces performance and memory overheads. There are tags that need to be fetched, and they need to be stored somewhere. On the other hand, we have DRAM integrity protection. That's basically an essential part in server computing, because DRAM tends to experience faults, and we want to correct those faults. And DRAM integrity protection usually has a very low memory overhead. We want to keep the redundancy as low as possible. So yeah, these are two not really related technologies, but our contribution is that we show we can combine this integrity protection and the memory tagging. We perform a case study where we show that we can implement a wide range of tagged memory architectures with our approach, and we show for a certain tagged memory architecture that we can reduce the performance overhead by a factor of 20 on average. So first, let's start with a bit about background DRAM structure. So here we have a CPU, and the CPU has a memory controller. And this memory controller communicates with a dual inline memory module over some control bus and data bus. Control bus is used to send commands to this DRAM, and data bus is used to transfer the data. And on the DIMM, we have a bunch of chips, and each chip has some banks in it. And in these banks, we find the memory array, which consists of columns and rows of memory cells. So a memory cell is basically the smallest granule in memory that we have. It consists of a transistor, and it consists of a capacitor. The capacitor stores the charge, which represents the logical value. And the transistor is basically used as a switch to read and write from the cell. Now, DRAM is subject to faults. One of the reasons for that is that cells tend to leak charge. So we don't have perfect physical components. The capacitor will leak some charge, and also this charge is not constant. So it's affected by external influences like temperature or radiation, for example. And also larger structures in the DRAM might also experience faults. So if a single cell experiences a fault, this will affect a single bit. But if some larger structure experiences a fault, it will affect multiple bits. Now, there are faults that are more common than others. The most common fault variant is the single bit fault. So one cell leaks too much charge, and the value we read from the cell is not the value that we actually store in it. Note, in our paper, we only consider naturally occurring bit faults, so we don't consider Rowhammer-induced bit faults. There's a similar paper that does that. It's called CSI Rowhammer. I was a co-author of that, so yeah. But these DRAM faults are the reason why we use error-correcting codes in DRAM. And how that works is we add an additional or two additional redundant chips on the DRAM module. And these chips are used to store a checksum that is computed over the data that we write to DRAM. And we use this linear checksum to verify each time we read from DRAM that the data that we just read did not experience a fault. In the case that we find that there was a fault, we can sometimes correct it, but not all of the time. And if we read from DRAM and do not see a mismatch in this checksum, then we have to assume that no fault occurred. When we add these additional chips there, we also increase the bus width of the DRAM from 64-bit to 72-bit in the case of DDR4 DRAM. Now, there are some downsides to error-correcting codes when using linear codes, and one of these downsides is that the error detection is limited. The linear code has something that's called a Hamming distance, and if the error exceeds this distance, then it might not even be detected, or even worse, it might be miscorrected because the code thinks, oh yeah, this error is a different error that I can actually correct, which means that it amplifies the error that we see. Now for something completely different, memory tagging. Memory tagging is a nice approach that works by storing metadata for each allocation in memory. In allocation is basically some object that you have in memory that's aligned. And the idea of memory tagging is when we have this metadata in memory, on each access we will check this metadata if the access is actually allowed. So we enforce what's called a tagging policy. The tagging policy defines how we interpret this metadata and what we do with it. And memory tagging is usually used to provide memory safety. It can also be used to implement domain isolation. There's a wide variety of tagged memory architectures that each have their own tagging policies, their own granularities, and how they work differs greatly, basically. But they all have this thing in common, that they associate this metadata with the object stored in memory. So here we have the issue that we need additional storage. We need to store the tags somewhere, and the location where we do that is, of course, the DRAM, which means a portion of the DRAM will become unavailable for our applications because we have to store the tags. And even worse, we have to fetch the tags, which means that we put additional pressure on the DRAM bus because we perform quite a lot of tag fetches in some cases. So how can we combine these two approaches or these two technologies? One idea would be to steal bits from the linear code. So we reduce the size of the redundant information that we store and use these free bits to actually store the tag. Well, in that case, we will weaken the error detection, which is bad, and also we will weaken the error correction, which is also bad. So that might not be the best approach there. We can try to implicitly encode the tags, which means we would compute our checksum not only over the data, but we would also include the tag in there. So when you access the memory and you use a wrong tag, you will see a checksum mismatch. But here we cannot read the tags anymore. Aliasing is possible, which means that sometimes a tag mismatch can look like an error can look like a tag mismatch, and also the tag size is rather limited due to this encoding. So the takeaways for us here were, we want to explicitly store the tags because this will allow us to actually read the tags back from memory and to distinguish between tag mismatches and actual errors. And also we want to use a nonlinear function because if we use a linear function, the drawbacks are just too great. We will weaken the error detection and the error correction too much. So the basic idea of our design is this. We throw out the linear checksum and we replace it with a hash. And when I say hash here, I do not mean the cryptographic hash that fulfills some security properties, but the only property that we actually need here is a function that offers good diffusion. So when I change a single bit in the input, I want that each output bit has a probability of about 1/2 to change its state. And we compute this hash on a cache line granularity, and we include the tag in the hash computation. So by including the tag in the hash computation, we ensure that even if a bit fault occurs in the tag, we can detect the bit fault, so we don't consume a wrong tag value. Then we truncate the output of this hash and we store it with the tag in the redundant storage that we have on ECC DRAM. So what we gain here is tags are now readable because they are explicitly stored, and errors are detectable because when we read back the data from memory, we recompute the hash and we compare it to the stored version, and there it is probable that we see if an error occurred. Now, how can we actually compute the hash and what properties does this function need to have? One very important property is that the possibility of a collision should be sufficiently low. So in the best case, if I have an n-bit hash, I want the probability that two values collide to be 1/2 to the power of n. Also, this function should be quick to compute because, as you can imagine, we compute this function every time we read from DRAM. And if each DRAM request, if each read becomes super slow, then that's just not feasible to implement. So we investigate two structures here that are based on block ciphers. The first structure here on the top is not cryptographically secure, but it's a bit faster than the other configuration. So what we do here is we throw our data into these block cipher instances and we sum up the outputs, which will then be truncated and stored in the redundant chip. The other version here is basically a PMAC construct. This one is cryptographically secure, but it's a bit slower because the last block cipher invocation needs to wait for all other invocations to finish. So keep in mind, any function that offers strong diffusion is suitable if no cryptographic security is required. And given that we are just assuming to see randomly occurring, or not randomly occurring, but naturally occurring bit faults, we don't have an active attacker on this hashing scheme here. So now this is where it gets ugly, because when we move away from linear codes, error correction becomes a bit tricky. The First approach that we can take here is to perform a brute force error correction, which works by guessing possible error vectors, applying them to the data that we read from memory, recomputing the hash, and comparing it to the stored version. If they match, we assume that the error was corrected. If they don't match, we have to try again. Now, the issue is that the complexity of this approach grows pretty fast. So it's approximately exponential growth in the number of iterations and also, of course, in the time it takes. So how can we reduce this complexity? One approach that we investigated was to add additional parity bits, because if we add parity bits, they can help us to not directly locate the location of the error, but it can help us to judge where the error might be. So it tells us, okay, we don't have the complete cache line we need to search, but the first half of the cache line or the first 25% of the cache line. That depends on how many parity bits we add. A much more interesting approach, however, is when you consider how DRAM errors look like. So if we think about a single stuck pin error, when we read from DRAM, the distance between the faulty bits will always be the same. So we can limit the search space rather strongly, and this allows us to correct, for example, an 8-bit error. If we do that in the brute force approach, that just takes about a year. If we do it in the pattern-based approach, it takes less than a millisecond. So I would call that a good improvement on that side. So we can see how this pattern-based approach helps us to correct errors that would be too complex for a brute force approach. It also works for up to 16 bits, which is way out of range what we could do with brute force there. Then we performed a case study where we tried to implement tag memory architectures with our approach. So we found out that we can come up with a nice table that doesn't use any vSpace hacks. We can implement a wide range of tag memory architectures while still offering some kind of error detection and protection. For example, if we implement ARM MTE, we can come up with a scheme that uses 8 parity bits, which means we are guaranteed to catch single-bit faults. It also uses a 40-bit hash that allows us to perform a lot of error corrections, so a lot of error modes are actually correctable by that scheme. And we can implement ARM MTE without any additional need for tag fetches or tag writes, because it's all stored in the ECC with the checksum, or in the redundant chip with the checksum. Also, we investigated 3 theoretical models where we increased the size of the tag. So model A, B, and C here are basically used to find out the limits of our approach. And we find that we can go up to a tag size of 51 tag bits while still offering a bit of error correction and detection. So a wide range of tag memory architectures can be implemented, many error patterns are correctable, and combining tagging with hash-based integrity protection seems to be feasible. I think I'll need to skim over the performance section here, but we modeled our scheme in the Gem5 simulator. The red bars here illustrate what happens if you store tags separately, so like regular tag memory architectures do, and the blue and the orange-ish bar here illustrate the performance that we get when we do this hash computation and use our approach to store the tags next to the hash. So in conclusion, replacing ECC with a truncated hash allows us to co-locate tags in this additional chip that's usually used for linear checksums. We can eliminate the storage and tag fetch overheads, and we can still offer error detection and error correction. So thanks for your attention, and I guess the floor is open for questions.